Okay, good evening. It's Dr. Jensen. Tonight we're going to talk about quantum mechanics. So, for a general chemistry class, this is stuff that is boiled down quite a bit to create a very easy structural picture of what the electrons look like in an atom. Okay. One of my favorite quotes about quantum mechanics, again from Richard Feynman, the same professor that I gave other videos from his lecture series. That, you know, if you think you can understand quantum mechanics, you don't understand quantum mechanics. And so it is incredibly difficult. It is usually high amounts of calculus in order to even begin to get to what we're trying to get to for the quantum mechanical models, right? So what we have here are probabilities of electrons, okay? Where might we find electrons, all right? So what we have here are three different ways of depicting the probability scales or where we might find electrons, okay? So the quantum numbers is one way. And so you should be able to determine if quantum numbers are allowed or not, okay? You're not gonna have to come up with quantum numbers, okay? We'll talk about this in a minute, but you won't have to make the quantum numbers. I will give you quantum numbers and you just have to know whether or not they're allowed or not, okay? And so knowing whether or not they're allowed or not is a lot like determining whether an address is correct, okay? So if I say the address for the campus is 3600 Little River Turnpike, Fairfax, Virginia, 90210. Okay, well, you know, the campus isn't in Fairfax, it's in Annandale, and the zip code isn't 90210, right? So you would say that's not a correct address for the campus. So that's how the quantum numbers are going to work, is you will have a quantum number, set of quantum numbers, and you're basically going to have to tell whether or not it's allowed. You will be able to determine electron configurations for an element. So again, these are generally posed in two different ways. Either I give you an element and I want to know what the electron configuration is, or I give you the electron configuration and want to know what the element is. And then there are energy diagrams. Again, the way that these are generally asked are, given an element, what is the corresponding energy diagram? Or here is an energy diagram, what is the corresponding element? Okay. All right, so quantum mechanics is from physics and chemistry. Again, here we are looking at the motion and interactions of subatomic particles, electrons, right, for the most part. So here we're dealing with things that are so incredibly small that they fall below our classical mechanics and physics, okay? So Newtonian physics breaks down as you get too small, right? As things become incredibly small, it begins to break down. Or when we look at things that, and this happens anywhere, and a lot of times in any kind of science, is when we start getting to the fringe boundaries of our limits of detection, things begin, our understanding becomes a little grayer, or our models break down a little bit as we start getting into extreme conditions, okay? And so quantum mechanics begins to explain how do we deal with these things where the sizes are incredibly small, the speeds are incredibly fast, and where we didn't have to use standard Newtonian physics in order to, I mean, that works fine for, you know, a tennis ball, but not so much for an electron traveling at the speed of light, okay? So we have to develop this new model in order to better understand the behavior of the electrons, okay? Now, again, in bulk, we can come up with bulk ideas of how things interact with one another, but as we get into nuanced arguments or nuanced interactions between molecules, we see things that we don't expect from like a macro level, right? And so what we have were, you know, Heisenberg, Schrodinger, and Born, who were working similarly in the same kind of arenas, working together, collaborating, and developing the models to define, how electrons move. And so what you have there is, what you see there is what we call a wave function. Okay, so Schrodinger and Born have the mathematical models, right, that we generally will see more often. Okay, so though that psi thing is actually an entire equation all to itself. Okay, and the H with little peg above it, right, is an operator. And again, these things are looking at probabilities, and these are very complex math, right? So I'm just going to go ahead and assume that everybody catches all of this, right? So, this is what those models look like. And again, it's a lot of differential equations where we're trying to boil down the probabilities of where the electrons are. Okay, so if you got all this written down in your notes real quick, I'm sure that everybody understands this. We'll just go ahead and assume that you've got this part. All right, so Niels Bohr, as he developed these models, so he looked at things as orbitals, that everything traveled in these kind of discrete orbits, right? So this is the model that I would draw if we were in class, because it's a very rudimentary look of how the electron is. So this is usually what we see is like, the thing in the middle with kind of just the rings around it like an onion, right? And so everything kind of travels in its little circles, and that's how it is. Now, or here it is, perfect. So this is kind of the Bohr model, right? Of everything has its little area. The electrons travel in a distinct level, and it makes sense. This explains a lot of the phenomenon, right? But it's not a truly accurate picture. Okay, and so there are a variety of things where things move to higher energy levels and then drop back down, and so we call those excited states. So for the most part, we're going to deal with things that are stable in their ground state, right? So our problems in this chapter will deal with the ground state energy, where it's more like this model where everything is, travels where it's theoretically supposed to be. Okay. And so, but what we have is, as energy goes into an atom, okay, so the inner ring here, so what you see here is the inner ring is a lower energy level. Okay, and so what you see is as the energy comes in from the outside, it knocks it up in energy. That's called excited state. So when it's in the outer ring, that's a higher energy level than the inner ring. So it took energy coming in order to excite it up into this higher energy level, right? But then as it drops back down, it releases off the energy. Okay, and so we have absorption and emission of energy from the atoms. Okay, now these absorption bands we find are fairly standard for the elements. Like most elements give off a standard absorption spectrum, right? When they are excited and when they relax back down, they give off energy within distinct patterns. And so this is generally how we tell things like, what is a nebula made up of? Okay, what is the atmosphere of a planet that we see out there made up of? Because we can tell the absorption bands of energy as we look at the light. We can parse out the bands of energy in the spectrum, and so we can tell what elements make up gas clouds throughout the cosmos. Okay, so we can use this kind of, this is spectroscopy. Okay, so we use things like spectroscopy to parse out and understand the elemental composition of various things because they have a standard excitation. Okay, when they are excited and they fall back down, they do so in these same similar patterns. Okay, so obviously I've already alluded to the fact that there were limitations, that the going around in a circle thing is overly simplistic. Okay, it's overly simplistic, and that there really wasn't a way of dealing with its three-dimensional orientation. Right, so it obviously doesn't look like that. It's a two-dimensional description. Okay, so what we're going to see here is this. All right, so we have the nucleus, we have, so the n value here is going to be our energy level. Okay, so every ring has a higher energy level. Okay, so if it has 3 rings, right, it takes a lot of energy to hold on to 3 rings. Okay, so n versus 1 is the inner ring, and then 2 and 3, and again, so this kind of builds like an onion model for these elements. Okay, so a more refined model was developed, and so we have the quantum numbers, which begins to describe the various aspects of an atom in a more refined way. Okay, and so we have these quantum numbers which describe various aspects of the electron movement. Okay, so the energy level, n, okay, is the rings that are formed. Okay, the angular momentum actually creates a 3-dimensional shape. Okay, so we're able to look at probabilistic shapes of electron clouds that are not, they just go around in a circle. Right, the magnetic moment looks at, well, what about this shape? Does this shape, is it always like, does the shape always just look like this? Or what if it looks like this? Okay, what if it moves around? So the magnetic moment is the orientation of that shape, okay, within a 3-dimensional space. Okay, and then the last part is the spin for the electrons. So like many, if we think of them as like magnets and stuff, the magnetic properties, the spin is positive, negative, kind of north-south kind of thing. You kind of think about it like that. That's essentially how it works, right? And so this creates a numerical representation of that takes into account these various aspects of the electron's movement, right? And so we have n, l, m sub l, and m sub s. Okay, so for our purposes here, again, you are not going to have to come up with these values. I will give you the quantum numbers. You just need to know whether or not that's a proper quantum number or not. Okay, all right, so let's talk about the rules for each one. So really, you need to know the rules for each one of the quantum numbers to determine whether or not it's allowed or not, right? So the principal quantum number is the energy level. Okay, what is allowed is any number greater than 1, right? Or 1, it can be any number 1 or greater, right? Because this defines the layers on the periodic table. Okay, where's my periodic table? Okay, so this really looks at the periodic table. Okay, so you see there's a 1, 2, 3, 4, 5, 6, 7. So it's talking about the layers on the periodic table. Okay, so the n defines the layer, the row that you're in. Okay, so it can't be 0. Okay, but any positive integer is technically allowed. Okay, now granted, our current periodic table only goes up to 7. Okay, so it's not likely that you're going to see examples that are beyond 7. Okay, but at least 7, 1 to 7. Okay. The next is the angular momentum, L. Okay. Again, this defines the shape of the orbital. Okay. This is a probability density. Now, the rule here is that L can be anywhere from 0 to n minus 1. Okay. So 0 is an allowed number, right? So if the n value is 1, then the only L value is 0. Okay. So it can't, so your L value cannot be greater than your n, right? So if I write the n value as 2, the L value can't be 3 or 2, right? It cannot be equal to or greater than the n value, right? So what we have here are, because these are shapes, okay, we have a variety of shapes that are associated with various electrons. Okay, so the first one is called the s orbital. Now you already saw the one picture here where these are the shapes here have a numerical number that's assigned to them as well. So the s orbital has an L value of 1 or of 0, right? So you look at the numbers here in a second, okay? So we can look at the numerical assignment of numbers, right? But the s orbital has a spherical pattern. Hang on, the image got, right? So the higher an energy level is really just the more layers of your onion, okay? So the s orbital is a spherical orbital, okay? And all the electrons in the alkali metals and alkali earth metals fall into this orbital. Okay, so all the alkali earth metals and alkali metals have a spherical orbital, right? And the further down they go, the more layers of their onion they have. Okay, the p orbital, right, has an L value of 1. Okay, so it has an L value of 1, and it has this kind of shape to it. And so in this shape, in the three-dimensional space, okay, so this one has some depth to it, whereas the s orbital had an L value of 0. So it only has one orientation. It's like if you take a ball, right? So if we go back here, if you take a ball and you rotate it around, okay, the ball looks the same no matter how you look at it, okay? Right? So imagine just a non, non-patterned ball, just a, spherical blue something, okay? And every time you rotate it around, it looks the same, okay? So that orientation is always, so that shape is an orientation doesn't matter. So the shape and orientation don't ever matter, all right? So we'll come back to the orientation later, right? But you'll see here that because of the p orbital shape, there are various orientations that it can have. You'll see this when we look at the next quantum number, okay? The d orbital has a variety of shapes, and the same thing with the f, okay? Because of all the electrons that it has kind of these very, interesting patterns that they take on as far as probabilistic clouds that they have, okay? Again, you don't really need to know these. It's more of just explaining what does the L value mean, okay? And so when we look at the L value, so the L value here you're going to see is broken up into these blocks. So here's the s orbital, okay, the p orbital, the d, and the f. Okay, so each one of these regions on the periodic table have different shapes. Okay, so if you are trying to determine what an electron is going to look like and how it's going to behave, it's going to behave different and look different based on its region in the periodic table. Okay. All right. So the magnetic quantum number, all right, m sub L, really looks at the orientation of the value in a three-dimensional space. So the rule here is m sub L can range from negative L to positive L. Okay. So let's look back at this orbital here, right? So the p orbital has an L value of 1. Okay, it's an L value of 1. So that means the orientations it can have are -1, 0, +1. Okay, so it is from -L to +L is the M sub L value. Okay, here's the M sub L value, -L to +L. So if my L value is 1, I have 3 various orientations, -1, 0, and +1. Okay, the d orbital in the middle, okay, the d orbital, okay, my transition metals have 5 different shapes. Okay, its L value is 2. That means the M sub L value can be -2, -1, 0, 1, 2. Okay, and so on. And then lastly is the M sub S value. Okay, the spin here only has a positive or -1/2 is all it's allowed. Okay, that's all the electrons have is an orientation of positive to -1/2. Okay, so these don't depend on any of the other quantum numbers. All right. So what you're going to see, now you're going to see this same kind of pattern come up when we look at the energy diagrams, okay, which we'll get to here in just a minute, okay, is you're going to see the spin written like this, okay, where you're going to see kind of this up arrow, but it's like a half arrow, okay. So this up half arrow is indicating the spin up or spin down, the positive a half or negative a half orientation of the electron, okay. But really for the quantum number here, the only thing you need to know is that the last value is either a plus a half or a negative a half. That's the only two, those are the only 2 options that it has, okay? And so now, because these are electrons, okay, they don't want to pair up to one another unless it's required, okay? So the up arrow is always going to be first when you see in the diagram, and then it will pair up with something else, with another electron, you know, when it has to, okay, when there's no more room, okay. All right, so some other rules that help us to define our quantum numbers, which this will more go into the next diagram here in a second, okay. So the s orbital can only hold 2 electrons, okay. The p orbital can hold 6 electrons. The d orbital can hold 10 electrons, and the f orbital can hold 14, okay. So these are subshells, all right? So think of it like shelves think of it like a bookshelf, right? So each shelf can only hold 2 books, okay? So you got to have a whole bunch of shelves to hold all your electrons, okay? So each position can't hold more than 2 electrons, and then they have to be opposite spins. Like it can't have 2 positives in the same place, right? Again, you'll see that when we look at the energy diagram. You'll see what I mean by that when we get to the energy diagrams. Okay. All right. So here are the summary of the rules that you would need. Okay. So if you needed to know, if you were studying 5 minutes for the 4 quantum numbers, this would be the slide that you would want to focus on. This has the rules for the quantum numbers. Okay. And any integer is possible. Examples 1, 2, and 3. These will correspond to the energy level. The L value can be any integer from 0 to n minus 1. The common examples are 0, 1, and 2, because these correspond to the s orbital, the p orbital, or the d orbital. 3 would be f. Okay. M sub L is any integer from negative L to positive L, which includes 0. Right. So like I said, if it's 1, then it's negative 1, 0, and positive 1. Okay. M sub s is the spin. It only has two orientations, either a positive a half or a negative a half. Okay. So what kind of questions do we have? You're going to have the quantum number. You need to determine if it's allowed or not. Okay, here's kind of a nice summary slide. Okay. Again, we'll come back to this one. It kind of summarizes all the different parts of what we're going to talk about here. You can see the M sub L value, or the L value is 0, the L value is 1, the L value is 2, the L value is 3. Okay. All right. I don't know if this is. I don't think I have this set up. So let's just look at the example. Let's not worry about trying to use the thing. Okay. So this is just an example here. All right. Which of the following quantum numbers is allowed? Okay. Again, it's not active, so you don't have to log in to do this particular question just yet. All right. I didn't get to that I forgot to get it set up before we started. All right. So given the quantum numbers here as choices, we just need to determine which one is going to be allowed. Okay. So the M sub s is the last number. All right. So it's N, L, M sub L, M sub s. Okay. So the M sub s can only be a positive a half or negative a half. So this one can't be allowed because the M sub s value is wrong. Okay. So let's go back to the first one, the n's, okay? Well, they're all fine n's, okay? You can have n values of 1, 2, and 3, okay? The L value ranges from 0 to n minus 1. So it cannot be equal to the n value, okay? So 2 is greater than 1, okay? So that's not allowed. 2 is equal to 2, again, not allowed. 0 is less than 3, that's fine. And 2 is less than 3. Again, that's fine. So we have a 50-50 choice here between these two. Okay, so these are not allowed because this value is equal to this and greater than the n value. So then the question is, then what is the M sub L value? So the rule for the M sub L is that it ranges from negative L to positive L. Okay, so if the L value is 0, then the only allowed value would be 0. Okay, again, it ranges from negative to positive this number. Okay, so 2 is not negative to positive 0. So if the value is 2 here, then 2 is an allowed value. And so this would be the only one that is allowed out of this group. Okay, similar question. Okay, the reverse
Wait, sorry, what was the answer for that one? The last one?
The last one, yes. 3, 2, 2, 1/2 is the only one that is allowed out of this grouping. Sorry.
How can we tell what the spin quantum number is? Like if it's positive 1/2 or it's negative 1/2?
Right. So the spin quantum number is the last one. It can only be a positive a half or a negative a half.
But how do we know like which one it is?
You mean if you're trying to tell it for a specific element?
Yeah.
We'll get to that. What you would tell that when you do the energy diagram. So you really can't. It's easier to come up with the quantum numbers from the energy diagram. So if you have an energy diagram of an element that you're trying to create the quantum numbers for, it is easy to generate the quantum numbers from a diagram that you have. But two things. Number one, you're not going to have to create the energy. You're not going to have to do the quantum numbers from an energy diagram, though you could. All right, but I'm not going to ask you that. And then we'll get to the energy diagram here in one of the next sections. Okay, so you'll see. We'll do an example of how you would come up with it if you were going to do it. Okay. All right. So the question here, second question is, which of the following is not allowed? Okay, so that means most of them are going to be allowed. All right, so again, you start from the M sub s. Okay, these are all fine m sub s's. They're either a plus a half or a negative a half. That's allowed for all of them. The n value is 1, 2, and 3. Again, it's an allowed value. The L value has to be less than, is from 0 to n minus 1. So it cannot be equal to n, right? That's the main rules. It cannot be equal to the n value, right? So 0 is less than 1, 2 is less than 1, 2 is less than 3, 1 is less than 3, and 2 is less than 3. So everything here is allowed based on the first three values we looked at. So it really comes down to the m sub L value, which ranges from negative L to positive L. Okay, so whatever the L value is, this value just can't be larger than. Okay, so it comes right back here to 3. Okay, 3 is greater than 2. So the value here that would be allowed would be negative 2, negative 1, 0, 1, and 2. Okay, but so 3 is the one that is not allowed. Okay, so it is the middle answer here because of the 3. Okay, it cannot be greater than this value. So the m sub L cannot be greater than the L value.
I have a question.
Sure.
So are there 4 quantum numbers in one bracket always? Always 4 numbers?
No. If you work practice problems in your book, they don't have to mention all 4. Sometimes they leave off the last one.
Oh, so will there be any case of missing L or M of L, like the ones in the middle?
No.
So they're always in the order of
Right.
NL, ML,
Right.
and MS.
Right. Yeah.
Thank you.
Usually they're always in the order that they're, if they give you quantum numbers, they're not scrambled. They're always N, L, M sub L, M sub S. Okay. Generally though, you may see practice problems in a book that don't list the M sub S, which it's not necessary for some problems if we're determining whether or not things are allowed. Sometimes the M sub S is not necessary for that part, but it has to at least give you the first 3 numbers. Right. So when you see my questions, they will have all 4.
Thank you.
Okay. All right. So the next way that we can look at this is an electron configuration, okay, which again is similar to the energy diagram, or is similar to the energy diagram and similar to the quantum numbers, but a slightly different way of tracking the electrons, okay? So this is a building up of electrons in a pattern, okay? So essentially we're going to list all of the electrons in an atom, okay? And so the way this is going to work is this, okay? So this is neon, okay? This is neon. Neon's electron configuration is this, okay? So you're going to read the periodic table, okay? So you're going to see how this is done. You're going to read the periodic table from left to right, starting from hydrogen. Hydrogen is in the first energy level. It is in the s orbital, and it is technically the first, it is the first electron. So there's 2 here right now because that includes hydrogen and helium. Okay, there are 2 elements in the first energy level, that is hydrogen and helium. Okay, so hydrogen would be 1s1. Helium would be 1s2. So the first number is the n value, the energy level, okay? The S listed is the subshell type. So we have S, P, D, and F, right? And then the number that goes with it is the number of electrons that you're counting in that subshell. So whatever element it is how far over you're gonna count, okay? So in the first energy level, in the s orbital, there are 2 electrons. Hydrogen would be 1s1, helium would be 1s2, okay? There's nothing else on that line. So just like if you were reading a sentence, okay, the number of the principal quantum number shell is n, end of sentence. the letter that designates the orbital type, the subshell L, and next sentence. A superscript number is that designated the number of electrons, etc. So you read the sentences left to right and begin the next sentence when you run out of elements.
Could you show us on the periodic table?
Sure. All right. So this is essentially a schematic of the periodic table. Okay. Hydrogen is right here. Helium is technically over here. Okay. So this is what I was describing the other day with the different periodic table diagrams, is that there are different ways. Okay. Is that helium doesn't fit in with the alkali metal family. Okay. Yes, it has, 2 electrons, but it's not, I mean, hydrogen doesn't really fit with, with the family of alkali metals either, but it has 1 electron that it loses. And so it is similar in electron structure to neon, or to sodium. Okay. But helium doesn't lose 2 electrons. Okay. Helium is more like a noble gas than it is an alkali metal. Okay. So helium is technically, again, we put it over here near the noble gases because it doesn't lose electrons. It doesn't lose those 2 electrons that it has like magnesium would. Okay. So, but that aspect doesn't fit with its orbital shell diagram, okay, with its orbital shell orientation. Okay, it looks more like an s orbital than it does a p orbital. So the organization of the periodic tables, those different periodic tables that you saw, those different pictures, we're trying to take into account, how do I create an orientation that takes into account these different variables? Okay, so our periodic table is not perfect. We have to understand where the limitations are. Right? For the electron configuration, helium sits over here. So we have 1s1 and 1s2. Okay, so if you were reading this sentence, that's all there is in this sentence. So where would you start the next sentence? Over here, right? We're starting on, we read left to right. Okay, at least we do here. All right, so we'd start the next sentence, 2s1, 2s2. And we'd read across, and now we'd be over here, 2p, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, which was the diagram for neon. So if I go back over here, where is my neon? Oh, there it was, 1s2, 2s2, 2p6, got me to neon. Okay, so here's 2p6 at neon. So what's my next one that I'm starting with? Okay, after I finish this row, where do I go? I start my next sentence over here. 3s1, 3s2, across 3p1, over to 3p6. Read my next sentence. 4s1, 4s2. Now here's where the tricky part becomes, okay? So we just talked about helium, how helium doesn't really fit where it is, right? Another problem is the transition metal elements, okay? Scandium, right? Scandium is right here, right? But scandium is actually in the 3rd energy level. So that means from an energy perspective, that middle block is actually shifted up 1, okay? So this is not the 4th energy level, okay? For this middle block is actually just, you take it and you shift it up 1, okay? But it didn't make any sense to put scandium right next to magnesium, right? Because the number of the proton count is different, okay? So it didn't make any sense to orient it, to create it that way. So it is where it is. So there's a slight energy difference here, okay? But we just read it left to right, okay? You just have to take into account for the difference, okay? You just read it left to right, okay? 4s1, 4s2, 3d1, 3D2, 4, 5, 6, 7 through 10. Okay, so it's 3D10. Then my next one here is 4P1 through 4P6. Start my next sentence. 5S1, then 4D over to 4D10 and 5P. Okay, so you see this. So this is the method that you will find that it takes. Okay, there's the 1S1, 2S, 2P, 3S, 3P, 4S, 3D, 4P, 5S. Circles around again and again. All right, so there's your F's over here. There's your 4 and 5F, right? Again, the F orbital is again shifted up, right? So it's not, all right? So here's right where that spot is. It is not in the 6th energy level, okay? It is actually in the 4th energy level, right? But again, how do you design a picture that takes that into account, right? That's what they were trying to do with those other designs, was try to take that into account. How do we create the periodic table so that it takes all these different things into account? Okay, so you only have to take things into account by reading left or right. Okay, this is the pattern that you need to follow. Okay, now that being said, you're probably not going to get down to the 4 Fs. We're not really going to have any of the F orbitals as examples, at least not at this stage. We don't really need to do that. If you can do, you know, a 4D or a 5P, that's more than sufficient to demonstrate that you know how to do this. Okay. All right, so here's an example, okay? On the quiz or test, right? I tell you, here is lead, okay? Here is lead's position on the periodic table. I want to know, what is its electron configuration? Okay, so let's look at where lead is. All right, so lead is right there, so lead's right here, okay? So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, through 5d, so 6s, and then it'll do the f, d, and then back over here to p. All right, so you got the F's, the 4 F's, and then the 5 D's, and then the 6 P's, right? And so you'll see this is its full total written out diagram, okay? Again, this is more complicated than you're gonna see on the test, okay? You don't have to write these, right? You're not gonna have to write electron configurations, okay? You just would have to pick this out as the proper electron configuration. Okay, so how do we find, so if this was given if we're looking at lead, right, and this was given as one of the answers, okay, so obviously there's going to be 4 other choices here, right, in a multiple choice quiz. So what you're going to look for is this, that the s orbitals have all 2s in them, the p orbitals have 6s in them, the d orbital has a 10 in it. The f orbital has a 14 in it. And the last number is the right count, that everything is in the proper order. That's what you're looking for. And what you're going to find is, say this is answer A. Answer B is going to be 1s3. Everything else is the same except it says 1s3. So you'll know, well, s orbital can't have 3 electrons, so that one's wrong. And then you'll look at answer C. We'll have the entire thing, but it'll be missing the 4D. It'll go 5S, 5P, and then everything else is the same. So you say, okay, it's missing something. That one's not right. Answer D is going to be exactly the same, except it'll be 6P3. So you'd say that one's not right. It's too many electrons. All right. Right. This is the other version. Okay. This is the reverse. If I give you the electron configuration, what element is it? Okay. So if we're coming up with what element it is, you want to go to the last digit. Okay. This is the one here. Okay. This is the one you got to look at to find out what element it is. 4s2. Okay. So you come over here to the fourth energy level, find the s orbital, and pick the second electron. Okay. So calcium is a 4s2.
For the quiz, would you give us this kind of table, how it's shaded?
No. You're just gonna have a regular periodic table. Okay. At least that's what I'm gonna give you. Presumably that's the one you're using. All right. So yeah, it's not gonna be shaded like this. So you'll have to know that it's oriented this way. Okay. All right, now you're in luck because there is a shorter version. Okay. For lead, okay, if we're looking at lead, right, you wouldn't have to write out this whole thing. Okay. There's what's called the noble gas configuration of this. So what it means is if we take lead, okay, here's the lead electron is 6p2, and we go backwards to the previous noble gas. Okay, the previous noble gas to lead is xenon. Okay, so we put xenon in brackets and we say from xenon, we start our configuration from xenon. Okay, so this shortens everything down. So all of this stuff right here, all this would get cut out. So we'd say all of this is going to be xenon's electron configuration. This is all xenon right here. So we're just going to put that in brackets. And then we start counting from the noble gas. Okay. So this is another way that you'll see the same thing. Okay. Is it'll start with a noble gas and say, from this noble gas, we're going to start counting from here. Okay. All right, so let's look at the last two questions and then we'll take a break here. Again, this is the way that you will generally see these questions, at least on the quiz or a test, right? Is given an element, what is its electron configuration? Or given an electron configuration, what element is it? Okay. So here's the example that I was alluding to before. Okay. Which one is the proper electron configuration for iron? Okay. So we got to have our periodic table. Okay. You have your periodic table, right? So this is probably in your book or you have a periodic table with you, right? So if we open up our periodic table, right, and we find iron,
It says
Fe.
bromine, I think.
Oh, sorry, it switched problems. Sorry, I accidentally hit the button. It switched problems. We're going to do bromine. Bromine's the second one. Okay. So we find iron on our periodic table. Okay. So iron is in the middle of the d orbital. Okay. It is in the first row, which we would need to know is 3d. Okay. So we would start from scandium. Scandium is 3d1, and we would count over until we hit iron. So 1, 2, 3, 4, 5, 6. So iron is a 3d6. Okay. So we're looking for an electron configuration that says 3d6. Okay. Well, there's 3d6. Oh, but here's a 3d6. All right. 3d10 is zinc, and 3d1 is scandium. Okay. This one doesn't even have a d orbital. Okay. That would be wrong. All right. So we got a 50-50 shot here. Okay. One of these is the proper one. So we'd have to look at, okay, well, is it written right? Okay, 1s2, 2s2, oh, here we go, 2p8. Okay, well, the p orbital can't have 8 electrons. The p orbital can only have 6 electrons. Okay, so D would be the correct electron configuration for iron. let's look at bromine, okay? We look at our periodic table again. We look over bromine, okay? So we find bromine in the 4th row, okay? Bromine is in the 4p, okay? So if we go over to the 4p, okay, the beginning of the 4p is gallium, Ga is gallium, okay? So we count over from gallium over to bromine, 4p1, 2, 3, 4, 5. So bromine is a 4p5 electron, okay? Bromine is 4p5, okay? So A is out, obviously. B is out. So we got 3 choices here for which one is written properly, okay? So let's start looking at them. All right, so we got 1s2, okay? 2s2, oh, all right, there we go. A 2s3, okay? The s orbital can only have 2 electrons. E is eliminated. C and D, 50-50, okay? So 2p6, 3s2, 3p6, 4s2, 3d10, okay, right there, okay? 3d8, okay, is not filling that orbital, okay? It wouldn't stop at 8. It would have to fill the orbital before it could go up to 4, okay? You have to fill up, the tank before you get to the end. Okay, so it's not going to stop at 8. So D would be the correct electron configuration for bromine.
On the graph, can you show where the placement of bromine is? I mean, I see it, but I thought it would be at 3pF, for instance.
So bromine is right here, right? So you have fluorine, chlorine, bromine.
So there's never a 1p, right? It just goes straight into 2p.
Exactly,
Okay.
exactly, yes. So the p orbital starts at 2. Okay, the only thing in the first energy level is just hydrogen and helium. So it would be a 4p. Okay, so the S and the P's follow the same order down. They don't have any changes. Okay, so the S and the P don't have any changes to their order. Okay. All right, so let's look at last one here. Okay, or two more, here, and then we'll take a break. All right. Here's the reverse. Okay. Given this electron configuration, what element is represented by this configuration? Okay. So here we would go to the last digit. Okay. Now where is the 3D? 3D is the row of scandium to zinc. Okay. Scandium to zinc is 3D. So we'd say, okay, it's number 4. So we'd start from scandium, 1, 2, 3, 4. And we'd count over 4, and we'd get to chromium. Okay, Cr is 3d4. Okay, so if you're counting, scandium is 3d1, titanium is 2, vanadium is 3, chromium is 4. Okay. All right. So this is another one that I don't have set up. So let's just look at this one as an answer here. Okay. Now this one's tricky. Okay. Again, given this electron configuration, what element is represented here? Okay. 3p6. Okay. So if we look over at our periodic table, the 3rd energy level in the p orbital, okay, aluminum starts the 3p. Aluminum over to argon. So if we count over 6, we'd get to argon. So is the answer none of the above? It actually isn't. Okay. There are 2 choices. Okay. Now, what subatomic particle are we talking about? Electrons. What happens when an atom loses electrons? It becomes an ion. So how many electrons does calcium have normally? Okay, I want you to look over at calcium on your periodic table. If you're looking at your periodic table, you should find calcium, number 20. So if it has 20 protons, it has 20 electrons. Now what happens if it loses 2 electrons? 20 minus 2 is 18. What other element has 18 electrons?
Argon.
Argon. So an ion can have, so ions can have the same electron configuration as a regular element, as a neutral element. So calcium, 2 plus, has the same electron configuration as argon. This is because argon is a noble gas. Argon is stable. That's why the electrons lose 2 electrons. That's why the alkali earth metals, that's why calcium and magnesium and strontium and barium lose 2 electrons, is because they want to look like the noble gases. They want to have the same electron configuration as a noble gas because the noble gases are stable. So how do they become stable? They lose 2 electrons. That's why when we memorize the oxidation state for the alkali earth metals, magnesium, calcium, strontium, barium were always +2. We didn't need to change their nomenclature because they don't ever have a +1. They are always +2. If they lose electrons, they're not going to lose 1, they're going to lose 2 because they want to look like the noble gases. Sodium, potassium, rubidium lose 1 electron. Because when they lose 1 electron, when potassium loses 1 electron, what element does it look like? It has 19. It loses 1, it now looks like argon. Argon is stable. It wants to lose specifically the right amount of electrons to look like a noble gas because the noble gases are stable. And so their electron configurations are going to look similar between ions and some neutral elements. Okay. What's another element that we could think of that has the same electron configuration as argon? Chloride. Okay. If chlorine gains an electron, it has the same electron configuration as argon. If sulfur gains 2 electrons, it has the same electron configuration as argon. Okay. That's why oxygen was always -2. Oxygen is always -2 because if it gains 2 electrons, it looks like neon. Neon is stable. The elements want to become stable. That's why things do what they do. They bond and they lose electrons to become more stable. Fluorine gains an electron. Fluorine's oxidation state is always -1. Because if it gains that 1 electron, it has the same electron configuration as neon. Okay. All right, so let's take 5 minutes here. Let's take just a 5-minute break here real quick. Let's refresh our drinks. And then we'll come back and we'll look at the energy level diagrams. And we probably are not going to make it too much further. So we'll probably just do a little bit more. We'll do the energy level diagrams and then we'll do the labs and things like that, wrap that stuff up pretty quick. All right. All right. So 5 minutes and we'll be right back. Okay, so the last portion is dealing with the energy diagrams, okay, which is really just the same thing as the electron configuration, just in obviously a diagram format. Okay, so here's a look at the energy diagram. Okay, once you know the electron configuration, the energy diagrams fill in the same way that the electron configurations did. Okay, now on a test, usually you don't get the full energy diagram, what usually will happen is they just cut out the highest energy level that's important. Okay, so if we're dealing with the 5s and the 5p, they would just be this segment is cut out, and that's all you get is the 5s 5p section. Okay, so that way it doesn't take up a whole lot of space. Okay, all right, so you'll see here 1s, 2s, 2p, 3s, 3p, 4s, 4p, or the 4s, 3d, 4p, 5s, 4d, 5p, the same order. Okay, so let's look back at hydrogen. Okay, so here is the electron configuration for hydrogen, 1s1. Okay, it is in the first energy level. It is in the s orbital, and it is the first electron. Okay, on an energy level diagram, it looks like this. The 1s has a single up arrow. Okay, now usually this is a half arrow. It's just, obviously I'm doing this in PowerPoint, and PowerPoint is for, I couldn't find half arrows when I was doing this, right? So usually it is a single up arrow. Okay, now when we get to helium, okay, here is helium's electron configuration, 1s2. Okay, so here is the electron or the energy diagram for 1s2. Okay, one arrow is up, the second arrow is down. Okay, again, one has to be positive, one has to be negative. Okay, you cannot have two that are positive. Okay, here's lithium. Okay, so here's now lithium's electron configurations down here at the bottom. Ooh. Go back. Okay, 1s2, 2s1. Okay, so we finished the first energy level, 1s1, 1s2, 2s1. Okay, here's beryllium, 1s2, 2s2. That is its electron configuration. This is what its energy diagram would look like. Okay, 1s1, 1s2, 2s1, 2s2. Okay, now here's oxygen. All right, so what you would get on the test is this. Okay, I would just cut out this part, the 2s and the 2p, because that's really all you would need in order to identify. So if I gave you the energy diagram, I'd say give you this, and what element is this? Okay, so if we're doing the electron configuration for oxygen, 1s2, 2s2, 2p4. And again, just reading the periodic table across, right? So 1s1, 1s2, 2s2. Now, when you get to the 2p, okay, when you're filling this in, okay, it is going to be 2p1 is an up arrow. Okay, 2p2 is an up arrow. 2p3 is an up arrow. Okay, each one of these segments, okay, each one of these shelves here can handle 2 electrons. Okay, so here's an individual shelf. It has 2 electrons in it. Here's an individual shelf. It has 2 electrons in it. The p orbital has 3 shelves, so it can handle 6 electrons. Okay, but when we fill those electrons into the energy diagram, the up arrows go first. Okay, why? Because electrons are negative. They don't want to pair up with one another. Okay, this is the electrons follow the guys in a movie theater seating pattern. Okay, they're going to sit every other seat until there's no more seats left over, and then they'll start sitting next to one another, right? So the electrons will be positive arrow, positive arrow, positive arrow, and then there's no more room, and then they start to pair up. So then the next one is down. Okay, so the fourth one is negative. All right, so it is incorrect. So what you would get here are incorrect versions of this, where these 2 are down, and then this one over here is also down, where it has the right number, but it's drawn improperly. Okay, and then so here we have fluorine and neon. All right, so let's look at how would we get the quantum numbers from this. Okay, so this is where I was alluding to before. You would kind of need the diagram to do the quantum numbers. Okay, so this is an energy diagram for, so it's 2s2, right? So that's beryllium. Okay, so the question is here. Okay, so here's the energy diagram. We had 1s2, 2s2. What is the electron configuration? The question is here, what is the quantum number for beryllium? Okay, so the first number is the n value, its energy level. Okay, well, it's in the second energy level. And so the s orbital, okay, the orbital value, okay, it's in the s orbital. The s orbital has a 0 L value.
Why does it have a 0 L value?
Well, because think of it like this, you know, it was called the s orbital, right? But it's like your social security number. You don't have letters in your social security number, right? So it's a conversion of the s, and so we're giving it a numerical value. So s has an L, s is the L value, it is 0. P, L value is 1. D, L value is 2. And F is 3. Okay. I'll go back to that summary chart here in a second. You'll see that again. Okay. So the different regions in the periodic table, and let me just go back to it. Different regions in the periodic table had different L values, right? Right here. Okay. So here's the s orbital. The L value is 0. Okay. So anytime you need to fill in the L value, instead of putting L or putting S, we put 0. We put the number in there. So there's a number that corresponds to S. There's a number that corresponds to D. There's a number that corresponds to P. Okay? And there's a number that corresponds to F. Okay? So each region is given a numerical value. Okay? So because we're talking about beryllium, okay, beryllium is in the s orbital, so its value is 0. Okay, the m sub L ranges from negative L to positive L. Okay, well, if it's 0, the only value is therefore 0. So 0 is an orientation. Okay, if you're a sphere, you only have one orientation, and we're designating that orientation as 0. Okay, the second electron for beryllium is down, so it is the negative 1/2 electron. So this would be the quantum number for this electron. We're looking at each electron. So there are 2 electrons there. Beryllium was the second one, and so it is the down or negative 1/2 spin. Okay, let's look at this one. Okay, first off, what element is this? Okay, what element is this? All right, so we go 2p, it has 1, 2, 3, 4. Okay, so we looked at this one. This one's oxygen, right? It has 4 arrows, right? I think my chart got slightly off. No, I think I just picked that out. I think I picked that particular electron, but it's so these, to go back and fix this slide. All right, so if you look at this, yes.
So how do you know what that element is for this, the one you just did, the negative 1/2? How do you determine the element from the values given?
From the quantum numbers?
Yeah, from the quantum numbers.
Well,
is that possible or no?
Yeah, you can. I mean, it takes a little bit of practice, and you'd have to kind of, I mean, you're essentially, you have to equate it to so if you're doing this, I mean, you'd look at the second energy level. Okay, so again, you're looking for an electron address, right? So there is only one element that has this quantum number. Okay, so you'd go to the second energy level. Okay, so the second energy level has everything from lithium over to neon. So there are eight elements within the second energy level. So the question is, we need to narrow this down to one single electron. Okay, so the L value says, well, it's in the s orbital, right? The L value is 0. Okay, so the L value of a 0 is only the s orbital. So that means in the second energy level, in the s orbital, there are only two possibilities. Okay, we got a 50-50 choice: lithium or beryllium. Okay, 2-0. Okay, the designation of 2-0 tells us it's either lithium or beryllium. That's it. Okay, it's one of those choices. Okay, the extra 0 here doesn't tell us anything. Okay, then the -1/2 would be the second electron. So we would essentially come down with, of lithium or beryllium, the -1/2, because again, it fills up positive first. So lithium is the +1/2. Beryllium is the -1/2. All right, so if you had to do it, all right, so let's look back at this number here, all right? 2, 1, -1 plus 1/2, okay? Let me, okay? So we want to know, what element is this, okay? So you could do this from the energy diagram, or if we were doing it from, if you were doing it from the quantum number, which you don't have to, but if we were, okay, the second energy level. Again, you have lithium all the way over to neon in the second energy level. But here, the L value says it's a 1. The L value with a 1 is the p orbital. Okay, so this automatically, so 2 and 1 already narrows down our field to a smaller geographic region. So 2, 1 is somewhere between boron and neon. Okay, so automatically this eliminates lithium and beryllium as an answer. Okay, so the -1 here has more meaning. Okay, because these are different orientations. +1, 0, and -1 were the values that were allowed in this energy level. Okay, in the L orbital, or the p orbital, you could have -1, 0, +1 right here. +1, 0, -1 are allowed values that you might have. Okay, so, but I'm looking at the -1 orientation. So that's over here. Okay, and it's a +1/2. Okay, so it is the third electron really here. So it's harder here to tell us with, it's easier to do it from this diagram. So it's the third electron. So if you look at over the P, so the first one is boron, carbon, and nitrogen. Okay. So this would be the energy diagram for nitrogen and the quantum numbers for nitrogen. Okay, again, you're not going to have to come up with the quantum numbers for the electrons. You're not going to have to tell me what element this is, and you're not going to have to come up with this from the elements. You're going to focus on the energy diagram, where if I give you this energy diagram, I would say what electron, what element is this, and you would tell me this is nitrogen. Okay, again, you don't have to draw energy diagrams. The two kinds of questions you'll be asked: what element has this diagram? Or given a diagram or several diagrams, you can tell me what element is it. Okay. So here's our question. What element is indicated with this energy diagram? Okay, so just like when we're doing the electron configuration, we go to the highest level. Okay, 5p is the highest level. Okay, so on your periodic table, right, the 5p is everything from indium to xenon. Okay, So we're going to count how many electrons are there in the 5p. 2, 3, 4. So we're going to count over 4. 1, 2, 3, 4. Okay, so indium is 1. Okay, tin, antimony, tellurium. Te, tellurium, would be the fourth electron in the 5p. So Te, option C, is the right answer. Okay, same kind of thing. What element is indicated by this energy diagram? Okay, the highest level is the 4p. Okay, so 4p is everything from gallium to krypton. Okay, gallium to krypton, 4p. So we count how many arrows do we see in the 4p? 2, 4, 6. Okay, so that's 4p6. So we look at our fourth energy level, we count over 6, and we get to krypton. Okay, krypton, 4p6. All right. Apparently, I do not have the opposite question of this, which would be, given an energy diagram or given the